cools at 25 degrees afterwards. Because we're trying to cool the air inside the car. Because really, we have the air at 55 degrees going to air at 25. This is what we're really trying to do. Okay, so note that the air, delta E for the air, should be greater than 0 or less than 0. Since the air is cooling. Yeah, less than 0, but delta E for the H2O liquid going to H2O gas, that should be greater or less. Yeah, probably greater, because we're going from liquid to gas. Okay, so this is one way to do this. Now another way to do this, you can take a different path if you want. So the other path that you could take, if you're going from H2O liquid at 55 degrees to H2O gas at 55 degrees. See, the other way you can do it is based on the quantities which you can look up, is you can say, okay, I'm going to heat up this H2O liquid to H2O liquid at 100 degrees, which is the normal boiling point of water. And then once you get to 100 degrees, the H2O liquid boils or vaporizes. And then once you have the H2O gas at 100 degrees, then it cools down to 55 degrees. So this is another path you can take to do this calculation. So when you're calculating Q and W are called path functions because those two quantities are determined by the path you take getting from your initial state to your final state. And then the thermodynamic properties, delta E, delta H, delta S, and delta G, those depend only on the initial and final states. Okay, so that's more of that abstract thermodynamics for you. So again, it doesn't matter what path you take. Because really, from my point of view, your path from Hartnell is to get to your bachelor's degree up here. So I don't really care whether it takes you, 2 years or 4 years, or they're going to take you 10 years. Whatever path you take, as long as you get from your initial state to your final state, that's the important thing. Okay. So let's see. Let's actually review. So the exam will cover equilibrium and thermodynamics. Now note that when we looked at energy and chemical reactions, that not only refers to thermodynamics, whether a reaction occurs, but how fast or how slow a reaction occurs. Let's answer this first question. We can determine whether a reaction occurs by which quantity, delta H, delta G, K, EQ, or lowercase k. Okay, so what I'd like you to do is to answer these 5 questions. Once you get an answer, share your answer with the person sitting next to you. See if you get the same answer. And then we'll review these answers in a few minutes. Looking up delta H. What about delta G? What about KEQ? What about lowercase k? Now what does lowercase k represent? Yeah, that's the rate constant. Now, whether a reaction occurs, what does delta H tell us? Yeah, whether heat is released or heat is absorbed. So that doesn't really tell us whether a reaction, although it is one of the driving forces. What does delta G tell us? Yeah, whether a reaction is spontaneous. So does delta G tell us whether a reaction occurs? Yes. Yeah, so again, if delta G is less than 0, that means that a reaction occurs spontaneously. Okay, so delta G less than 0, this means we have a spontaneous reaction. Now what does KEQ tell us? Yes, we know that equilibrium constant tells us the ratio of, so that's the concentration of the products divided by the reactants. So and reaction has a large KEQ, that means that there's more products or more reactants? Yeah, more products. If there's a small KEQ, that means there's more reactants and products. So does KEQ tell us whether a reaction occurs? Yeah. So we have a large KEQ. That means we have more products. Which means that the reaction occurs. So we didn't talk about this, but there is a relationship between delta G and KEQ. So that relationship is this equation. Okay, so we have delta G is equal to minus RT times the natural log of G. Yeah, so this equation relates equilibrium constant and delta G. So again, this makes sense because if KEQ is large, that means delta G should be less than 0. If KEQ is small, that is, if it's less than 1, delta G should be greater than 0. So for the first question, note that we can tell whether a reaction occurs by looking at both delta G and KEQ or one or the other. Rate constant doesn't tell us whether a reaction occurs. This just tells us how fast or how slow the reaction occurs. Okay, how are you guys doing on the second question? We can determine how fast the reaction occurs by, who says it's 1? Who says it's 2? Who says it's 3? Who says it's 4? How are you guys doing on the third question? We can determine the amount of products formed by looking at yeah, so who says it's 1? Delta H. What about number 2? Yeah, it's by looking at that formula. Yeah, so who says number 3? Yeah, so KEQ tells us the amount of products formed, but we know that KEQ is related to delta G. What about 4? Rate constant. Yeah, that doesn't really tell us how the amount of products formed. Yeah, so note that for the third question, delta G and KEQ tells us the amount of products formed. Okay. A large KEQ means delta G is, yeah, so it should be 1, 2, 3, or 4. It should be 3, less than 0. And then for the last one, as the temperature increases, rate constant increases, KEQ increases, delta G increases, or it is hotter.
It is hotter.
Yeah, so it's got to be number 4, it is hotter. Does anything happen to the rate constant K as temperature increases? Yeah, so as the temperature increases, the rate constant K increases. Now, is there a formula that we use that relates rate constant to temperature? Okay, so this was way, way back before exam 1, and that formula is yeah, so that equation, I think Juan used that as the Arrhenius equation, so A times E to the minus EA over RT. So as the temperature increases, the rate constant K increases. Now, does the equilibrium constant increase as the temperature increases? Okay, so let's just say we have some generic reaction. A plus B goes to C plus D. And we know that KEQ is equal to C times D divided by A times B. So if the temperature increases, does the equilibrium constants stay the same? Because they call it equilibrium constant.